So today I will cover a regular solution model, but let first see what are the different models available and mostly useful in thermodynamic properties of solution. Okay, so first is ideal solution, where we have assumed that there is a random mixing and there is no interaction between the atoms. That's why the enthalpy of mixing is 0. But in regular solution model, the, the enthalpy of mixing is not 0. Still the mixing is assumed random, so delta Sm, that is entropy of mixing, is same as ideal. But in case of quasi-chemical approach, we assume two atoms as a pair, and that is a separate entity. Okay, so that's why its entropy and enthalpy both are different from the regular solution model, and it has different formulas regarding that. uh, as a matter of fact, you also need to know that a regular solution model is often also called zeroth order quasi-chemical model. So what is the assumption, basic assumption for a regular solution model? So whatever the composition of A and B, it will not affect the interatomic distance and bond energies. Okay, suppose we have xa mole fraction of A atoms and xb is the mole fraction of B atoms, and we have made a solution, and the enthalpy of pure A, if there is no mixing, before mixing, enthalpy of A is number of AA atoms into energy of AA atoms, right? Let me first put the pointer, and here you can see that enthalpy of pure A is number of AA atoms into energy of AA bond, number of AA bond and energy of AA bond energy, it is nothing but the bond energy. Similarly, enthalpy of pure B is number of BB bond and energy of BB bond. And if they go into the solution, then you have to find it out or figure it out, what is the number of AA bond into the solution into energy of AA atoms, AA bond, plus number of BB bond into the solution into bond energy of that kind of atom, plus number of AB bond into the solution into bond energy of AB kind of bonds. Now 1 mole have Avogadro number of atoms, that is capital N, and if we have a regular solution model, then definitely there will be some AA bonds, there will be some AB bond, there will be some BB bond into the solution. So we have a atoms which is surrounded by some other atoms, and the number is nothing but the coordination number, that is assumed as Z, and this is the average coordination number. Locally it can vary, but overall we have find out that the average coordination number is Z. The number of AA bond in pure A material will be n into xa is the number of A atoms multiplied with the coordination number, and as there are same kind of atoms, then we will introduce a 0.5 factor, and when they go into the solution, 0.5 is due to the AA kind of bond, and we have how many number of AA atoms? N into mole fraction. If 1 mole have n atoms, then xa mole fraction will have n into xa number of A atoms. Now in a solution, if you have a Z coordination number, so it is not like that all the coordinate will be surrounded by same kind of atom. There may be some A atoms, there may be some B atom, and that the probability of occupying a particular side by atoms is depend on the mole fraction of that kind of atom, right, and number of coordination number. So that's why Z into XA is coming into the picture. So a number of AA bond into the solution is 0.5 into number of A bonds, and the probability of having those sites, coordination site filled with A atoms. Similarly for B atoms is like that, and there is no 0.5 factor when there is a AB kind of bond atom. This is the number of A atoms, and the corresponding probability of having a B atoms is Z into XB, right. So now we put this value in this equation. Okay, enthalpy of solution and enthalpy of pure, and we find out the change in entropy due to mixing is the nothing but enthalpy in the solution minus enthalpy of pure. Now if we put into this equation this minus this plus this, okay, then we will figure it out. The value is nothing but this. Okay, if we do the calculation, we will get a value which is now Avogadro number into coordination number into mole fraction of A into mole fraction of B, and this is the difference in bond energy after the mixing. Okay, there is energy of AB bond energy, and the average bond energy of AA and BB bond, and if we subtract that value, then it is represented as difference in bond energy epsilon, and if we put it, then we will get omega, which is nothing but NaZ into epsilon. It is called partition function. So delta H mix is nothing but omega XA XB. Okay, you need to remember this equation for our further derivation. Now one important observation of this equation is that delta H mix is equal to omega XA XB. Now if we do derivative with respect to XA and XB, and we figure out the value of this derivative at extreme point, x is equal to 1 and xb is equal to 1, then we will find out the slope of that curve. Derivative is nothing, will give the value omega. This omega is the partition fraction, is a finite value, and previously we have also find it out the slope of this curve at the extreme corner, right. This delta minus t is RT XL and XA and XBL and XB. If we do the derivative of delta X mix with respect to the mole fraction at extreme point, then we will figure it we already derived it that the slope is infinite, right. So delta H mix can be negative, positive both, but suppose our delta H mix is positive, omega value at extreme point 0, when the mole is 0 mean pure, then if we add a very minute amount of B atoms, the delta H mix will be positive, but the delta S mix will be very large at 0 infinity, at minute element you can understand it will be very large. So the solution is favorable, right. That's why the delta G mix will definitely first go down, then it will rise up, and the value of sigma the value of omega will determine this point. Okay, this will either shift or this side, that is depending upon the omega value. But there is definite that at temperature higher than 0 Kelvin, if only at 0 Kelvin we get delta G max positive. So at temperature above 0 Kelvin, no solution is pure. Okay, you cannot separate it out A atoms or B atoms, whatever you do above 0 K. There will be a preferable tendency of formation of solution. Thermodynamically, at 0 Kelvin, we can say that a solution will separate it out as AA atoms, BB atoms, or pure AA, pure B portion. But kinetically, it is not possible due to no diffusion, right? So now we have a clear picture of the Gibbs free energy for a regular solution model. Mechanical mixture XAGA plus XBGB plus enthalpy of mixing omega XAXB plus entropy of mixing RT XLN XA plus XBLN XB. Now we can write XA XB, this term, as XA square plus XB plus XB square plus XB, because XA plus XB is equal to 1, right? XA plus XB is equal to 1. So if we take the common, then we get XA plus XB into XA XB. So if we just put the values of these, then we can write G as omega XA plus omega, sorry, not omega, mu A XA and mu B XB, where mu A is GA plus omega 1 minus XA square plus RT ln XA, and omega mu B will be similar like that. If we just put the value, then we will get G is equal to XA mu A plus XB mu B, and the mu A mu B value is given here. Now this mu is similarly like the chemical potential in case of ideal model, but we have a extra term mu A 1 minus x square, and to form it as the same in form in case of ideal solution, we can write it mu A is equal to GA plus RT ln A, RT ln A. Okay, we are not deriving it, just assuming this whole value is equivalent to this value. This whole value is equivalent to this value, which will give this equation, right? ln A minus RT ln A minus RT ln x is nothing but omega 1 minus x square. So this is equivalent, we have assumed it. Okay, or you can rephrase it that we have given a new term in terms of mole fraction. We are getting a unique term that's called activity, which is taking care of the portion of Gibbs free energy that is taking into the contribution when A is going into the solution. Okay, so what here you can see that this mu A naught is nothing but GA for pure A atom. This is the Gibbs free energy, but when it is going into the solution at a composition of X, its Gibbs free energy has been decreased. Gibbs free energy has been decreased to a value mu A into Xa, mu A into Xa. Okay, and the decrease, which is this decrease, is nothing but RT ln activity. Okay, so this is nothing but mechanical mixture of this value and this value, mu B XB and mu A XA, right? So this value RTLN activity of A in alpha phase is this value is also equivalent to this value. Clear? Now what is this A? What is this new term A? This is called activity, and it is taking care of the interatomic attraction, and this also you can say that it is a true composition. Okay, due to the mixing, our composition due to the mixing of AB atoms, the effective concentration of A has been changed from its mole fraction. It has been changed due to the interatomic attraction between the different kind of atoms, AA or BB or AB, like that. So let's understand what I am trying to say by this figure. There is a solution of A and B atoms, and we have heated temperature is it is room temperature, where A atom has been created a vapor pressure. Now if there is no interaction between the A and B atoms, two different kind of atoms, we will get a vapor pressure PA. But if B atoms don't like A atoms surround itself, it's repelling the A atoms, then what will happen? More number of A atoms will be in the vapor phase. Number of A atoms, concentration of A atoms in the vapor will increase, and that's why the vapor pressure will also increase. So the true concentration of A atoms has been changed due to introduction of some another kind of B atom and its nature of attraction or repulsion. So that is the activity. And if you add very minute element of solute in a solvent, and if we gradually increase it, then when it will have the solute is becoming a solvent, then it will try to follow the mole fraction. That is Raoult's law. Activity is Raoult's law. But when it is in dilute, it will definitely follow Henry's law. This is one observation you need to see. Okay. Now the conclusion of our thermodynamics of mixing lecture is that we have able to derive it out, the free energy of mixing delta G mix for a regular solution model, and minus T delta S mix will always give a negative value because delta S mix is positive, and if delta H mix is negative and the temperature is high, then we will get a delta mix is like that. And if the temperature is low, the T delta mix will go upward, and that's why the delta G mix will be reduced. On the other hand, if the omega is positive, when the omega is positive, another thing you need to understand, when the omega is positive, when our epsilon is positive, if epsilon is positive, mean that epsilon AB is more than AA and BB average of that. So AB atoms, the bond energy of AB atoms is higher, mean it will not to decrease its energy, it will try to clustering of AA and BB atoms. Okay, so when there is a clustering of A and BB atoms, then delta G H mix will be positive. Delta H mix is positive, means it is endothermic. And if the AB bond energy is less, mean it will try to mix. Okay, A atoms try to surround itself with the B atom. There will be ordering, or also called mixing, of AB atoms, At that condition we will get delta H mix as negative value, and delta H is mix is negative value, mean it is exothermic. Okay, so this four possibility we can see. Now when we try to do the phase diagram, we will have to, at every temperature we have to draw this kind of Gibbs free energy diagram of two phases, and they will attain equilibrium. How they will attain equilibrium, let's understand it. So we have a composition x naught where the Gibbs free energy of beta phase is GB naught and Gibbs free energy of alpha phase is GA naught, and definitely we can see that GA naught is lower than GB naught. So B will transform to alpha. Okay, the equilibrium phase is alpha, but is there any way I can get more low Gibbs free energy? Yes, it is. We have a possibility. What is that? If you have a mixture of alpha 1 composition of alpha phase and beta 1 composition of beta phase, then the mechanical mixture of these is giving low free energy from both the pure value, and this G is getting decreased when we are drawing a curve like this and this and this, and ultimately when there is a common tangent between this alpha phase and beta phase, we will get the lowest value of Gibbs free energy, and that is the Gibbs free energy equilibrium, GE. X naught composition will try to decompose to alpha phase with a composition of alpha E and beta phase with a composition of beta E, equilibrium composition, and it will provide the lowest Gibbs free energy, right? Now phase diagram. So this is the phase diagram. This is also called isomorphous phase diagram, where and they completely mixed each other. So there is a liquid, there is liquid plus solid zone, and there is a solid phase. So at a temperature, higher temperature, we have a liquid stable, so liquid have a lower free energy like this, and solid have a lower higher free energy. And at a temperature Tm of A, so Tm of A is which one? This one, right? This is the Tm of A. At that temperature, what is happening? Both solid and liquidus have a single temperature where both are stable, mean the Gibbs free energy is same. So this is the definition of melting point also. So at melting point, the liquid and solid have same Gibbs free energy, equal Gibbs free energy. And similarly, in case of TMB, we will get a curve like this. In between a temperature, we will get T2, where first there will be solid stable. So the Gibbs free energy of solid should be lower at T2. This is the solidus curve. So Gibbs free energy of solid is lower up to B composition. Then we will get a mixture of composition should be lower, and then we have a liquid composition. Okay. So I think you have understand. Now if we have a now another thing I want to share, that when there is alpha phase or gamma phase like this kind of Gibbs free energy, we will get equilibrium composition, and this point in the phase diagram look like this. So you have seen iron carbon phase diagram. So this is the AE1 line and this is the A3 line, and in between there is a line which reflect these points at different temperature. This is called T naught temperature, and it has a very useful application of this T naught temperature. I will explain it later on, I think. So first understand how this kind of phase diagram we will get, where we will get a miscibility gap. right? What is happening here? We have a liquid stable at a temperature, okay, shown here. Then at T2 temperature we have a liquid stable, solid stable, then solid plus liquid phase stable, then solid stable, then again solid plus liquid stable, and then solid stable, right? And as our temperature is decreases, as our temperature decreases, our solid is trying to separate it out with between with two phase who which have different atomic what it's called, different lattice parameter value, okay. So solid is stable, one solid is stable, then there is a sharp rise of the Gibbs free energy, there is a sharp rise in the Gibbs free energy, and then again another solid is stable. In between these two solid we have a mixture of alpha and alpha phase, okay. Here the lattice site and lattice parameter value is different, here the lattice parameter value is different, and in the in this zone they are trying to separate it out, okay. They are trying to form a mixture of these two. Now let's we will try to understand what are the possible Gibbs free energy diagram for this phase diagram at T1 temperature. First we will get alpha phase, then alpha plus liquid phase, and then liquid stable, okay. So you can see there is a alpha phase, okay, there is a liquid plus alpha phase stable, and there is a liquid stable, and in this temperature there is no beta phase, there is also beta phase here, there is no beta phase stable. That means the Gibbs free energy of beta phase is way higher than this alpha and liquid phase, which can be shown here, right? Now at T2 temperature, here we can see there is a two zone, liquid plus alpha and liquid plus beta. So there will be two curve like this, here and here. In between liquid will be stable, and this curve is like this, and in between we have a liquid zone. So actually what I try to say is this, there is zone and there is zone, and between liquid is stable, okay. Now at T3 temperature, where liquid is directly converting to alpha plus beta phase, it is called eutectic reaction. So at this line is the equilibrium with alpha, beta and liquid, three phases at the same temperature. So what is there, that this line which is representing equilibrium of two phase, now it has to be touching the three phases, one common tangent for three phases. So what I mean to say, this is one common tangent for three phases, and below a composition there is alpha stable, and below another composition there is beta stable, and liquid will be in between that two phase diagram. And you can understand what could happen for T4. It is clear that liquid will be increases, and then alpha and beta we will get a composition of alpha beta equilibrium. So one thing you need to notice, that with increasing in temperature, dg by dt is equal to minus s, right? dg by dt is equal to minus 8 at constant pressure. dg is equal to vdp minus s dt. We know that mean the slope of the g versus t curve is negative, right? Slope of the g versus t curve is negative. That's why if we decrease the temperature, as we decreasing the temperature, our liquid line is going up, right? Liquid line is going up. All are going up. Decreasing temperature or increasing temperature gives your energy is decreasing. Increasing temperature gives your energy decreasing, or decreasing temperature, all the lines are going up, but their rate are different. That's why we are getting so many kind of gives your energy diagram to form a phase diagram. Now another important observation you need to understand is that we have, in case of regular solution, we have derived that delta G mix is equal to delta H mix plus delta S mix, but both the enthalpy and entropy are overestimated by this process. How? When we are considering the mixing of A and B atoms, they have different lattice parameters, so there is a lattice strain energy. Due to this different lattice value, there is a strain energy associated with the mixing, and we are not considering that enthalpy into the enthalpy that will contribute a part in the enthalpy. And as there is a mixing preference, A or B kind of this kind of mixing preference, similarly our entropy will not be that much. It will also have some low value. It has not totally random mixing. That's why the enthalpy is decreasing. Okay, entropy is decreasing, and due to the not introduction of that strain energy, delta H mix is also quite high. So that's why we can say that both are overestimated, and as both are overestimated, delta G is equal to delta H minus there is a minus T delta S mix. I am trying to say that there is a contribution of enthalpy and entropy, and as there is a negative sign in between, that's why the both have overestimated and they are cancelling out, but they will not cancel out with the exact value, but their sign are same. That's why we can say that it is the delta G mix given by the regular solution model is not so much wrong. Okay, there is definitely some overestimation on both the enthalpy entropy, but their sign convention is same. That's why they are neglecting out some values. Okay, now in case of at higher temperature, in case of any higher temperature, the A and B atoms are totally mixing to each other, because at that higher temperature minus T delta S mix will dominate. Whatever the enthalpy value, there is a mixing preference. But we have seen that if there is a delta H mix, enthalpy mixing is positive, then delta G mix in at a some composition, they will try to rise. Delta G mix is positive, right, at low temperature. So as temperature is decreasing, the enthalpy positive is taking effect onto this matter. So if this enthalpy mixing is very high, okay, there is a very high tendency of surrounding a particular atoms by some other atoms. Here we cannot distinguish at higher temperature whether this site will occupy by copper or Au or Au's or gold atoms. So but as the temperature decreases, if the partition fraction has a very high value, then there is a preferential tendency of occupying this side by either Cu atom or copper atom, like this. And this way we can get a super lattice. This is called super lattice. So this is a order disorder transformation. Here is a disorder, there is a order. So as the temperature is decreasing, there is a order disorder transformation, and we will get a super lattice by doing this. So this is copper surrounding gold, or gold both the way possible, as we will get a particular a composition like CuAu superlattice or Cu3Au superlattice. So in case of solid solution, what happening? In case of solid solution, there is not any preferenceable site to occupy. So that's why our delta G mix is have a wide range, right? But in case of intermetallics or particular structure, there is a sharp decrease in Gibbs free energy at that composition. This is the Gibbs free energy of intermetallic, like cementite Ni3Al. Okay, another important thing you need to understand this, there is some special name of these intermetallics, like Ni3Al forms this kind of superlattice, where this white atom will be aluminum and this black atom will be nickel, and this is called L12 superlattice. Okay, now what is the temperature effect on solid solubility? So there is a Gibbs free energy diagram here, you can see. Okay, so the B atoms, as when the B atom is very minute element, so this is the solute, you can see a solid solution of B atoms, and with the increasing in temperature, the solubility of B atoms is increasing in the alpha phase, right? So the chemical potential, you can see the chemical potential Xb is stability of beta phase is very narrow. That's why the Gibbs free energy is a sharp increase like this. Okay, it's like a intermetallic, like cementite. Okay, cementite, there is a sharp increase. Let's assume B is a carbon and this is a cementite. So at temperature T1, we can see first there is alpha phase stable. So this is alpha phase stable, right? Okay, okay, so first there is alpha phase stable zone, and this is alpha plus liquid zone. So we have not shown the liquid phase here. The temperature here we have a, and then we have a alpha plus beta stable in this temperature range. So in this composition range, we have alpha plus beta composition, where beta has a fixed composition and alpha has equilibrium composition of this, right? I think you can understand this diagram clearly. Now if you have understand, let me tell you that we have drawn the common tangent to represent the equilibrium, and this common tangent, the mu b chemical potential, the mu b chemical potential of B in beta phase is same as the Gibbs free energy, right? And at that composition, our Gibbs free energy of alpha is this value, right? And mu b in the alpha phase, mu b in the alpha phase, chemical potential of beta in alpha phase is this, where I am pointing out. So this is nothing but from the equation I have derived previously. We can see this is the GB alpha plus omega 1 minus x square plus RT ln x. Now if we replace the GB alpha and mu v GB beta with mu b, I forget it out, but so much